Hey guys, Esky here. Here at the Fell Design Lab, we got the Electron sling. The harmonizer just got its third coat of latex, so I'm letting it dry out. This is our Synchrotron video. So I mount the Synchrotron at an angle into the laser housing like this and line it up. What happens is when the laser is placed normally, the beam gets sucked into a magnetic field of the synchrotron by entering at the bottom of that tube, and it follows a parabolic distortion circular pattern to the other edge in a loop like this that kind of sags here, and it gets, over time, the appendage of the magnetic field gets energized and interlocks with the magnetic field of the laser, and it can build up 1/10 of a megawatt from the 3000 watt mode of the laser. The constant beam mode with the finished project, including the harmonizer, has a constant beam mode of 3000 watts, which is actually a lot safer in this form when tuned to visible light than any other. Because it's a microscopic 1 micrometer filament. This basically would not even hospitalize a person for days or weeks of constant exposure on the spot. So ordinarily, this is our synchrotron. I do want to say I'm going to be doing some advanced particle physics experiments and whatnot to see if this beam is actually made of 50% matter, contains a high amount of ZP elementary particles. But this synchrotron will be good for that because as a parabolic circle, it probably can distribute and work as a mass chromatograph for elementary particles. The heavy particles would dip down right here. The light particles would come out around here. And also by wave shaping with the electron sling using the wavetable functionality, we may be able to create a focus point which will be brighter. So I'm going to try that. And I'll program a wave structure. The tuner is the waveform, and the envelope is the charge button I found out. The play button is the red button, and you can also play it as a pulse. The memory will sustain until the charge button is released and held again. We're going to try to create a focus at the bottom, and we'll see if we can see a halo. So there's our envelope. The pulse will reset the memory of the device. This should still sustain its memory, so here we are. Running the synchrotron. The beam is definitely flowing now. It has good curvature. Let me try it again just to see. It's not generally going to be safe to pulse into the synchrotron until the beam has been flowing for about 30 seconds, so remember to use a backstop. But here, I'll see if I can create a better foci. I do see one halo at the bottom though. The halo is definitely denser at the bottom, so actually it looks like we succeeded. As I look at it with the naked eye, I can definitely tell there's a suspension that's very well tuned at the bottom. it moves, but it centers at a balance every 5 seconds for about 15 seconds on a 20-second cycle. No, it's a 5-second cycle, but it spends 3 seconds there. Here it is again. Yeah. That's a nice halo. I'll see if turning off a light helps. 1 second. Well, there we have it. That's the experiment. This halo can get very bright over about 30 minutes. It probably will make a glow on the table. I have yet to try it. But I have confirmed the power of the beam. I can inject a pulse now. Because I'm still holding the play button, the memory is still sustained in this case. The beam is quite strong now. I can see a significant glow. The frequency has shifted to about 3.5 seconds. But yeah, that's our Synchrotron, or Slynchrotron as we'll call it. Thanks for watching, guys. Yikes. Ow, yeah.